Okay, welcome. We're going to talk about measurements, our first dimension of space-time, that dimension of length, and a little bit about our conversion lab and the expectations for that. First of all, dimension of length we call capital L, the abbreviation, with big brackets around it. When we speak generally about length, you're already familiar with many units used for describing the length or space in one line that something occupies, and those common units are centimeters like we've used in class, meters, which is the base unit, inches, of course, kilometers, miles, and the light year are very common units of length in science. And we will be using the MKS system, meter, kilogram, second, system of international standard units, and so that base unit for length is going to be the meter. The length dimension is one of 7 fundamental dimensions of the universe, and it has one of the 7 fundamental units associated with it. That associated unit is the meter. As an example, the other of the main 7 fundamental dimensions that we will look at soon is time. The fundamental unit that corresponds to the dimension of time is the second. Okay. We will look briefly at our one measurement tool for length that is common that we need to be absolutely super good at using because we will use it frequently in the lab. We need to be able to recognize the difference between our inches and centimeters, and that is also on our meter sticks as well. So given some example here, my red line there, I've indicated inches are on the top of my ruler. The red line shows the 0 line. That's where I need to start a measurement. Okay, notice that the measurement can't start where the physical end of the ruler is. It needs to start where the 0 line is. I have some object, the purple line, that I will measure the length of, and so I'm sure to have my line of vision directly on top of or level with the end of that thing I'm measuring, the purple line in this case. I've drawn a little golden line there to indicate where it falls upon the ruler. And so the question is, how do we measure this? Well, it's clearly 2 inches, but more than 2 inches, but less than 3. And we need to notice the increments or intervals that occupy the space between the 2 and 3 marks. And there are 16 of those marks in between the 2 and the 3, and that means that each one represents 1/16 of an inch. So I can count the number of those marks, which I will do now, and it looks like 13 and a half of those marks. Okay, halfway through is 8, then I have 9, 10, 11, 12, 13, and I'm going to estimate down to half of a 16th of an inch because that's the precision we are allowed. You make some estimate that is below the smallest distance. So the smallest distance on my ruler is that 1/16 of an inch distance, and you can see that my golden line there falls about in the middle, somewhere in between the 13th and 14th tick mark, between the 2 and the 3 inch marks. So I'm estimating at 13.5 or 13 and a half 16ths of an inch. I divide that out just using my calculator, so I get a decimal value. So that's 2.84 when I round it. 2 inches and 84 hundredths of an inch. So you've done a conversion from 16ths of an inch into hundredths because we need to express it in decimal form. And we have a base 10 decimal, that's what decimal means, is a base 10 expression of fractions of 1. So this is one example of why we don't use the imperial or English system, because dividing something up into 16 parts is just annoying to deal with. We'd much rather have things just split up into tens because our decimal system is already split up into tens. There's an example of taking a measurement for inches. Now let's flip the ruler over the other way like we did for our lab, and we're looking at the centimeters now. Okay, so in my centimeters, I again take the red mark and line it up at the beginning of my measurement of the purple object, and I line it up such that it is at the 0 line, not at the end of the ruler, unless that's where the 0 line is. For our big meter sticks, that's where the 0 line is, at the end of the stick. For these smaller ones, it's where the line is. I've drawn my purple line to indicate where it's stopping. It's clearly more than 4 centimeters, but it's a little more than 4. So I look down to the next interval between the 4 and the 5. Those are the millimeter marks, of which there are 10. Hence I wrote 1 millimeter is 1/10 of a centimeter. There are 10 millimeters for every centimeter. So between 0 and 1 centimeters, I have 10 millimeters. So now I can try to make an estimate for my measurement. I'm also going to mention now that 1 millimeter is equal to 1/1000th of a meter. Milli, think millennium, 1,000 years. Millimeter is 1,000th of a meter. Not 1,000 meters, but 1,000th. All right, so anyway, this measurement here, I've zoomed in and I've seen that I have 1, 2, 3 millimeters past the 4 mark, 3 smaller tick marks past the 4, and so that means I have 4.30 centimeters. 4.30 centimeters. I've underlined the 0 there because that's the level of precision I have. I'm looking, does my golden line there that measures the purple length, does that golden line fall in between 2 different millimeter tick marks, or does it fall right on top of one? And I can measure down with a precision of 1/2 a millimeter. If it's somewhere in between, I'll say it's 0.35 if it's between the 3rd and the 4th millimeter line. But it looks like it's just on the 3rd millimeter line past the 4. So I mark it as 4.30, indicating that I've measured it to that 3. I've rounded it right there. That golden line, if I zoom in a little bit, it may be just a tiny bit below. Like maybe it's really at 4.29 centimeters. It's 4 centimeters and then 2.9 millimeters. But I don't have that level of precision. I can only go, the convention, the rule is, I can only go down to a precision of 1/2 of what the smallest measurement on my ruler is. So the smallest measurement on my centimeter side of the ruler is the millimeter, so I can only round to 1/2 of a millimeter. That's why I have 4.30. That's where your significant digits come from, by the way. When you were told how many significant digits does it have and why do they have this 0 at the end of it, it's because we just rounded to that place. So there in green, that's the 3 millimeter. My measured purple value is 4.30 centimeters, and I told you that 1 millimeter is 1/10 of a centimeter, so there it is in the 10th place. 3 millimeters, it's in my measurement, 3/10 of a centimeter, that's why it's in the 10th place. This is also my purple final measurement, equivalent to 0.0430 meters. I've converted the centimeter value to meters. And so notice we said that the millimeter is equal to 1/1000th of a meter. Millennium is 1,000. So there's the 3 underlined in green again in the 1,000th place. Notice now also my 4 is in the 10th hundredths place because it's 4.3 centimeters and 4 centimeters. Centi, think cents. There are 100 cents in a dollar. There are 100 years in a century. So that 4 centimeters is in the hundredths place because it is 1/100th of a meter. Okay, lastly, I think we're going to look at just what those common units are that I really want you to know for the labs. It's a repeat of what was on the first slide. Dimension of length is the capital L in brackets when we generally represent it, and there are many units for that length. The most important ones that we use in the MKS, meter, kilogram, second, International Standard System, are the kilometer at the top in red, which is 1,000 meters. We have the meter, which is the base unit, which is equal to 1 meter. The centimeter, which is 1/100th of a meter, as I mentioned, and the millimeter, which is 1,000th. The last little thing then, since we have done our conversions lab, you are expected to have a data table from measuring your centimeters and inches of those lengths. So I have my objects 1 through 10 in black. I skipped 4 in my listing, but there they are on the left, and then I want you to clearly have labeled centimeters and inches. Notice I can abbreviate my units at the top of my column so I don't have to repeat them at every row. Please do that. Number 2, I should have produced then a graph, y and x axes there for you. Put centimeters on one axis, inches on the other axis, plot that data given your data table. Draw a line of best fit the way we discussed. Select 2 points on the line that are not data points and use those points to determine the slope of that line. There's your slope formula. Remember that we have this symbol, the triangle, that means delta or difference in. So y2 minus y1, my final y minus my initial y, can be expressed as delta y. Same for x and delta x. And when I have that slope m calculated that way, I should get a number that I've boxed in orange. Do me a favor and show me 2 places past the decimal. Round it if you need to. Fourthly, check your result number 3 using Desmos or a scientific graphing calculator. We've practiced this in class, and refine your slope if necessary. I want to see both you having produced this value or determined this value of the slope manually in step 3, and I want you to be able to, and show me that you did, check it by using a calculator or graphing utility. This value is the value that I expect to see boxed, just like my orange value there, or my black value is boxed in orange, and that's what we'll submit for your result for this lab. See you next time.